Welcome to video 27 on the TTb course. This video is from part 6 of the course. In part 6 we wrap up. In this video we take a look at some of the challenges involved in using a conventional real-time operating system, or RTOS, and we consider some alternative TT designs that provide support for task preemption. The material in this video is based in part on Appendix 9 and Appendix 10 in the ERES2 book. As usual, I would suggest that if you haven't read these appendices, you do so now and then watch the video again. So we spent some time in this course considering what we can do with a tick list. And this is the core of what a TT system is about. So we began the course by saying that a TT system involves releasing at least one set of tasks according to a predetermined schedule. Because we're releasing the tasks in accordance with a particular schedule, we can model the system behavior very clearly and determine key things such as the system response times. We've looked at such issues in previous videos on this course. What I'm going to try and do in the present video is explore some of the ways in which we can do roughly equivalent things, roughly equivalent kinds of modeling in designs that are based on an RTOS. And then, having done that, I'm going to go back and say, okay, what can we do with a TT system that supports task preemption that makes it more like a design based on a conventional RTOS? So what we're going to look at in this video are systems that involve task preemption. We're going to look at some of the challenges involved in supporting task preemption in a design that includes a conventional real-time operating system. And we're going to look at some of the ways in which TT designs that support task preemption can avoid some of the challenges that arise with a conventional real-time operating system. Let's start with some basics. We're going to start by looking at a schedulability test for a set of tasks that are executed using a conventional real-time operating system and for which we want to apply a rate monotonic analysis. So these are going to be rate monotonic designs. I will explain what that means very shortly. So let's begin by saying that a typical RTOS is based on a fixed priority preemptive schedule. What this means is that we assign a priority to each task. This priority remains fixed while the program runs. Whenever it makes a scheduling decision, the scheduler tries to run the highest priority task that is ready to run. And this task will run to completion unless it's preempted. So we end up with a scenario that looks something like this. So here we have what we can view as the input to our system. So this is the system input. So if you like, we've got three tasks here: a high priority task, a medium priority task, and a low priority task. So this is what we'd ideally like to happen, but we'll assume we have only a single CPU. So we can't run all of the tasks at the same time in this form. Instead, we obtain this output, this behavior from the system as shown below. So here we have our medium priority task running for a while until our high priority task is ready to run. Then the high priority task runs to completion. Nothing can interrupt it because there's nothing on the system of higher priority. Once the high priority task is completed, then the medium priority task completes. It does so even though there's a low priority task due to start executing at this point in time roughly, but the execution of the low priority task is delayed until this point in time. The same process applies in these later stages. So we end up with behavior that looks like this. In most designs, this behavior will be dynamic, in that there will be particular events that cause, for example, this high priority task to be released, and this release of this high priority task will not always be periodic, or not necessarily be periodic. This is what happens in a design with fixed priority preemptive scheduling. And in most cases, the trigger points for these task releases will be asynchronous events. So the task releases will be event triggered. So how do we assign the priorities to our tasks? The most common way of doing this is using a rate monotonic model. This sounds much more complicated than it is. So a rate monotonic model means simply that we give processes with the shortest period the highest priority. So let's assume that we are dealing for the moment with periodic tasks. So the sets of tasks with the shortest task period would be given the highest priority. So for example, if we've got a task set like this, where the tasks have a period of 1, 12, 20, 50, let's say these are in milliseconds, then the priority assigned to these tasks would be 1, 2, 3, 4, where 1 is the highest priority and 4 is the lowest priority. So we're assigning the priorities based on the task periods. The shorter the period, the higher priority. So most frequent tasks have the higher priority. Tasks that are called less frequently have a lower priority.
There are two things that we need to review before we can consider what an RM model means when we're developing our systems. The first is we need to consider how we represent systems of periodic tasks. So as a reminder, we've been representing these tasks with a tuple, which is a set of parameters. And the key parameters we've been considering are the period, the worst case execution time, the deadline, and the offset. And we've considered this in several previous videos. We've also considered the processor utilization measure. So we've said that we can calculate the processor utilization, or the average CPU load, for a given set of periodic tasks as follows. We sum up for each task the worst case execution time divided by the period. We take the total of that sum of worst case execution time divided by period for each task, and that gives us the utilization. And we know that we cannot schedule the task set if the utilization figure is greater than 1, because no processor can be running more than 100% of the time. So we've seen the example at the bottom of this slide before. If we have just two tasks, task 1 and task 2, T1, T2, represented by their worst case execution time and their period. Task 1 has a worst case execution time of 10 milliseconds and a period of 20 milliseconds, so it contributes 50% to the CPU utilization. Task 2 has a worst case execution time of 60 milliseconds and a period of 100 milliseconds, so it contributes 60% to the processor utilization. The sum of these processor utilizations is greater than 100%, U is greater than 1, therefore we won't be able to schedule this task set no matter what we do. Following those reminders, we can now look at the processor utilization test that can be applied when we're working with an RM schedule. So this assumes that we're working with an RM schedule, a fully preemptive task set, and we have an RTOS or a similar framework that will support this. If we have such a framework available, then we can prove mathematically that as long as our given task set has a utilization figure that's less than approximately 69%, then RM will give a valid schedule. Even if our utilization is greater than approximately 69%, RM may give a valid schedule. So what that means in practice is, if we sum up the processor utilization for the set of tasks in our set, and we find that the processor utilization is less than approximately 69%, then we know that we will be able to schedule that task set. This sounds very powerful. So what this means is, unlike a TT design, we don't need a tick list. We don't need the complexities of the modeling process that we've gone through so far. We simply need to measure the processor utilization. If this is less than approximately 69%, then our RTOS will be able to schedule the tasks. Overall, this sounds much easier than the kind of TT approach we've been discussing on this course. However, there are a couple of things you need to be aware of before you switch off this video and rush off and buy a new RTOS. First thing you need to be aware of is that RM has an assumption that the tasks are independent. That is, that there are no shared resources between the tasks. We'll talk a little bit about that in the course of the next few slides, but in practice it's very, very rare for that to be the case. The second assumption with RM is that the task deadlines are equal to the period for each task. Let's just remind you what that means. Suppose this is the task sequence that we expect to see. We expect to see our tasks released at these times. If we say that for task X in this case, that the deadline, the time at which we wish it to complete, is equal to the period, then this is a perfectly valid schedule according to an RM model. So we're saying here that as long as X completes its execution before it's scheduled to be released again, then this is a perfectly acceptable task release schedule under an RM model. So the assumption is that for each task, the deadline is equal to the period. What that translates to is lots of jitter, a very high level of jitter. And as we've discussed in previous videos, jitter in the release time of 10% of the task period can be enough to render the dataset unusable. And your system effectively, potentially uncontrollable with 10% jitter. Here we're talking about jitter that's in the region of 100% in the release times. Many people who use an RTOS are not necessarily aware of the underlying assumptions that are there when you use an RM on an RM analysis model with your task set. So let's consider the question of task independence, which is assumed in an RM model. In practice, tasks are very rarely independent in practical systems. Let's consider a simple example. Suppose we've got just two tasks in our system. Task H, which is high priority, task L, which is low priority. We're assuming that this is not a TT design, so that the tasks may be released at any point in time, at random times. So we don't know when task H will be released and we don't know when task L will be released. Suppose these tasks share a resource. Let's assume that resource is an analog to digital converter, and that task L uses channel 1 on the analog to digital converter and task H uses channel 0 on the analog to digital converter. This could be any other form of shared resource. It could simply be a data transfer between the tasks, which is almost always required in every practical system. It's very difficult to produce a practical system where you have lots of tasks where there are no data transfers between the tasks. And the same problems that we'll discuss with the ADC apply with any other form of shared resource. So let's just stick with the ADC example for a minute. Let's suppose that task L is using channel 1 on the ADC. This stage will assume there's no protection, no mutex, etc., if you're familiar with such terms, no protection of the ADC. So if we don't have protection of the ADC, then what will happen is task L could start using channel 1. Let's assume task L has set up channel 1, configured it to take a data sample, and is waiting for the data sample to complete. And at that point, task H is triggered. Task H wants to use channel 0 on the ADC. So task H has higher priority. It reconfigures the ADC to use channel 0. Task H is the highest priority task. It completes its ADC activity, gets the data that it needs from channel 0 on the ADC, and task H completes and finishes. Then control returns back to task L. Task L has no knowledge of what's happened in task H. All it knows is it is still waiting for a sample to come back from the ADC in channel 1. this sample will never be delivered because task H has reconfigured the ADC. So at the best, task L will time out because the data sample is not produced on time. Of course, we cannot allow this to happen. So what we will do is use a mutex or another form of simple flag mechanism to avoid the two tasks fighting over the ADC. And what that means is that when task L is using channel 1 on the ADC, it will lock the ADC. So when task H is triggered, it won't be able to use the ADC until task L has completed its access. Now task L may only require very brief access to the ADC, 2 or 3 microseconds perhaps, to complete its activity. But even for that time, task H will be blocked. It will not be able to obtain its sample from the ADC for that 2 or 3 microsecond period, and will have jitter as a consequence in the sampling that takes place in task H. In most systems, we might have many different tasks. Once you start adding multiple tasks into the mix, add mutexes or other protection mechanisms, it becomes very difficult to determine, even for high priority tasks, when we're going to obtain the data sample. And what we're describing here is effectively a form of priority inversion, in that there can be circumstances in this design when task H wishes to make a data sample. It's a high priority task, but it's blocked by a low priority task. In other words, the low priority task is given priority over a high priority task, a situation known as priority inversion, which can give rise to deadlock in your design. So once we start to have multiple tasks in our system, we can't simply use a simple RM model. We have to consider algorithms such as priority inheritance, priority ceiling, etc., to avoid us having problems with our tasks of multiple priority that can be triggered at random times. This is not a trivial problem. Even with the resources of NASA, the Mars Pathfinder mission in 1997 had significant problems that took a lot of effort to solve when they had a priority inversion problem in part of the system. Brutally, very few organizations have the resources to match NASA. If priority inversion can cause problems for an organization with this level of experience and knowledge, you have to wonder whether other organizations will necessarily be best placed to deal with these problems. Let's look at a couple of simple examples to explain where the challenges come from. So this is a simple 2-task example where we're sharing access to an ADC. What the slide shows is that we have some normal code and we have some code that accesses a critical section. This is a standard term. The critical section is a standard term for areas of code in which we access a shared resource. So this is what we want to happen in our design, we'll assume. So we're expecting that our normal code will run for our low priority task. So if we ignore the critical section for a moment, ignore the ADC, ignore the critical sections, what we would expect to happen without any of these complications is we would expect this task to run, the low priority task to run until we got to this point. Then we would expect the high priority task to run, and then we would expect the low priority task to complete. That is what we would expect to happen if there were no shared resources. Now we'll assume that we have a situation where the low priority task runs. It locks the ADC during its execution, and then we run the high priority task. So we end up with a situation that looks like this. So we have the low priority task running for the first 2 time periods. Then the high priority task kicks in. At this point, the high priority task can run and can interrupt the low priority task because the high priority task is running normal code. At this point, the high priority task doesn't require access to our ADC, our shared resource. Then, in the next time period, the high priority task will require access to our shared resource, but the low priority task has locked that resource. So we have to switch back to run the low priority task so it can continue access to the shared resource in this design. Once the low priority task has completed access to this shared resource, we switch back to the high priority task. It completes its access to the shared resource, the high priority task completes its normal code, and we return control then back to the low priority task to finish the operation off. It starts looking a little bit more complicated here. This is just two tasks, and we have a short period, as indicated in red here. We have a short period where the high priority task is blocked. So this is a form of bounded priority inversion. When we only have two tasks, we can calculate in advance, if we're willing to spend the time doing so, how long this task will be blocked for. In practice, however, we very rarely have just two tasks in our system. If we take this one step further and we add in a medium priority task into the mix. So now we have a situation where we have the low priority task running, the high priority task kicks in and runs while it runs normal code. Then the high priority task is blocked because the low priority task has locked this critical resource. While we switch then back to the low priority task to complete access to this critical resource. As we're doing that, before we finished access to the critical resource, which would be at this time, a medium priority task kicks in. This doesn't require any resource access. It has no shared resources, we assume, with the high priority task or with the low priority task, so it can run unimpeded. So it interrupts the low priority task, prevents the low priority task from completing access to the shared resource, which means that the high priority task cannot run, which means the medium priority task runs indefinitely. The end result may be a processor reset or some other serious failure in the system. This is a form of unbounded priority inversion, and it's more difficult to handle. We just consider a couple of other examples. We get into a deadlock situation, which is a problem that people often discuss. We get into a deadlock situation if we have multiple critical sections. So we have different shared resources, and we can quite simply end up in a situation where we have one task waiting for release of one resource and the other task waiting for the release of the other resource, and that is a deadlock situation in which the system simply hangs because nobody can carry on because everybody's waiting for somebody else to do something. So we can solve this, as you are probably aware. We can solve these kinds of problems by using some form of sealing protocol. So what we do in this case, if we go and look again at our system with two critical sections, while a task has access to a shared resource, we increase the priority of that task to be equal to the highest priority of any task that also requires access to that resource. So what we're saying is we started off with a design which had fixed priority scheduling. What we're saying is, to avoid the problems of priority inversion, we are going to change the priority mechanisms in our system so that we have variable task priorities. And we're saying that we will change the task priorities temporarily during the program execution in order to avoid the problems of priority inversion in our design. View that another way. What we're saying is, to avoid the problems of priority inversion, we are going to temporarily invert the priority of the tasks during the program execution. So to avoid major problems, particularly deadlock problems caused by priority inversion, we are going to deliberately change the priority of low priority tasks during the program execution. We'll do this briefly, we hope, in order to allow the system to continue without deadlock problems emerging. So our RM assumptions are that the tasks are independent and have no shared resources. This is very rarely the case in practice, and in order to deal with this problem and to avoid priority inversion, we have to employ sealing protocols in our design, which further complicate our model. And then we're saying that the deadline is equal to the period in an RM model, and this introduces a great deal of jitter. So overall, our simple model of RM scheduling with a conventional RTOS doesn't always translate terribly well into a practical design if we require precise control of the task timing. So if we use an RTOS and an RM model, it can be challenging to obtain precise timing behavior in our system. Are there alternatives using a TT architecture that would allow us to meet these requirements? Let's consider a couple of challenges in this domain. Suppose we've got a simple TTC design, then it's easy to imagine a set of tasks which can't be scheduled using a TTC architecture. Suppose, for example, we want to run the tasks illustrated in this slide. Our requirement is that we run task A, let's say, every millisecond, and we also want to run task B in the design, but task B has an execution time, worst case execution time of about 3 milliseconds, for example. We're going to face a challenge if we want to run these two sets of tasks, this set of two tasks on a TTC platform. More generally, if the worst case execution time of the longest task in our system is greater than the period of the most frequent task in our system, then we can probably not use a TTC scheduler. This applies to every mode in the system. Every task set in every mode, we have to apply this test. So for example, if task A has a worst case execution time of 10 milliseconds and task B has a period of 5 milliseconds, we may not be able to schedule these tasks using a TTC scheduler because task A will block task B. So all of the designs we've looked at so far on this course have involved a TTC scheduler. So sometimes we can find a solution to this problem. So we talked very early in this course about data structures that will allow us, for example, to send long streams of data between an embedded board and the outside world. So we said that the basic architecture we would probably use in this situation would be to copy all of the data that we want to send to a software or hardware buffer, and then to schedule a task to take one element from this buffer and pass it to the receiver, for example, every 10 milliseconds. And we discussed reasons why this would give us a means of greatly reducing the worst case execution time of our data transfer task. In some cases, this may be a way of addressing the problem. Use of the kind of techniques we discussed on the previous slide can allow us to reduce the number of times in which we need to support task preemption in a TT design, but it's not always possible to avoid task preemption. In general, I recommend that your system should use TTC tasks, cooperative tasks, wherever possible, because this gives lower overheads and therefore lower unit costs, greater predictability and therefore shorter testing times and higher reliability in many cases, and ease of certification where this is required. With appropriate design approaches, we can often reduce the number of designs which require task preemption, but in my experience very few developers manage to spend their working life without having to employ task preemption at some point, and it's important to understand how we can implement this. So let's see how challenging it is to add support for task preemption to a TTC scheduler. So this, in overview, is a TTC scheduler. So in this case, we have our dispatcher in function main, as we've seen before. We've got some initialization functions. We start the scheduler and we dispatch our tasks. We have our timer ISR here, and all that's doing in this case is updating our tick count variable. So, as you'll appreciate by now, this is a reasonable overview of how a TTC scheduler operates. All the tasks in this case are released by the dispatcher. Let's turn this into a time-triggered hybrid, or TTH scheduler. This is very easy to do. So our dispatcher remains exactly as it was before, and we've made one small change to our timer ISR within the scheduler. Now within the timer ISR we have a task call. A single task is called from our timer ISR in the scheduler. This is a very small change, but it has important implications for the design and testing and verification processes, and it has important implications for the way we put our system together. So the end result is that our system now looks something like this. So in this tick list we have A and B. These are standard cooperative tasks. These tasks will be released from the dispatcher function in main, just as we've done previously in all of our previous code examples. What we're also doing here, however, is we're adding in these preempting tasks which are released from the timer ISR. So as you'll see, and this is the behavior that we would expect to see, just after each tick, in this case, our preempting task is called. So at the start of tick 0, this has very little implication, very limited implications for our design. Task P will run from the timer ISR, then the dispatcher will be called, and in this case we assume that task A is due to be released at this time. What happens at tick 1 is slightly more interesting, however. We're assuming this time that task A runs for roughly 1.5 ticks, and we're assuming that's correct and expected behavior. Now, at the start of tick 1, we have our preempting task interrupts the execution of task A every time there is a tick, even if there's another task running. So task A is interrupted by the preempting task here, which has higher priority. Then task A resumes, then task B runs. Task B is also released by the dispatcher. Then at the start of tick 2, task P is also released. This is released from the timer ISR, from the scheduler ISR, and the process repeats. So in this TTH, or time-triggered hybrid scheduler, it differs from a TTC scheduler as follows. The first is a design assumption. The assumption that we made previously, that all TTC tasks will have a worst-case execution time that is less than the tick interval, is relaxed. The assumption that all TTC tasks released in a given tick interval will complete within the same tick interval is also relaxed. In addition to scheduling any number of TTC tasks, one periodic preempting section, PS, is also supported. The preempting section may be used to release one or more TTH tasks. The TTH tasks have a higher priority than the TTC tasks and may preempt or interrupt them. The TTH tasks also run to completion once executed. That is, the TTH tasks cannot themselves be interrupted by any of the other tasks in the system, including other TTH tasks. So that's what we've done to our system. We might now have longer tasks, longer TTC tasks that execute for longer than the tick interval. The sum of all the tasks released in a given tick interval may be longer than the tick interval itself. We can schedule some higher priority TTH tasks which are released from the timer ISR. All of the tasks, all the TTH tasks run to completion once executed. So as we put together a time-triggered hybrid scheduler, we end up with a system that looks something like this. We have, in this case, our preempting tasks shown in blue on this slide, and we have a single cooperative task shown in yellow on this slide. So periodically we transfer control between our cooperative task, which is interrupted or preempted, to our short preempting task, short higher priority task shown in blue. So this is an example of how our systic handler might look in such a TTH design. So here we're assuming that we may have some very long TTC tasks, perhaps with a worst case execution time of several seconds even in this design. And we have it's a TTH scheduler, so we call our preempting tasks from the timer ISR. So we're reading, in this case, we're assuming it's an emergency stop switch. So we've got some long cooperative tasks and we're reading an emergency stop switch, periodically interrupting that cooperative task to read the emergency stop switch. And we're also, just for illustrative purposes, adding in a heartbeat LED that is also set to trigger, in this case, flash on and off, change state every 1 second. It does this again using our high priority task, while our very long low priority TTC tasks are running in the background. Here's another task set to consider. Suppose we have these tasks. So we have A, B, C, and D, and we'll assume that these tasks are jitter sensitive. And then we have task E, which is not jitter sensitive. So we have the worst case execution time of these first 4 tasks is 2 seconds in this case, and our period is 10 seconds. So these tasks use up, in total, when we add up all of the task processor utilizations, we get to a total utilization of 95%. So we should expect that we can schedule this task set. How would we meet the jitter sensitivity requirements? How would we ensure that task A, B, C, and D would have low jitter in their release times? The way that we might achieve this is by running all of these tasks in sequence. So we run task A, task B, task C, and task D in sequence from the timer ISR. We have to do that because if we don't do that, the execution time of task E, which is 3 seconds, will cause significant levels of jitter in the timing for task A, B, C, and D. So if we use a TTC scheduler with this task set, we'll get a lot of jitter in our jitter sensitive tasks. If we use a TTH scheduler and release task A, B, C, and D from the timer ISR and treat task E as a low priority task that runs in the background as a TTC task, then we will obtain the required behavior from this task set. Let's consider another factor here. So we've said that if we use an RTOS, we're making an assumption that the deadline is equal to the period, and we may have a high level of jitter in our task timings. So what happens to the task jitter levels in our TTC and TTH schedulers? So in this case, this is a review of data that we've seen previously. If we use idle mode in a TTC scheduler, we've seen in previous discussions, and it's discussed in detail in the book, that we can reduce the jitter level in the ticks in our system, usually down to a level that's too low to measure. So effectively we get 0 jitter in our designs in a TTC scheduler, in most cases on a modern processor, if we push the system into idle mode at the end of the dispatcher. So what happens in this case, however? If we have a TTH scheduler, then we can't achieve that. Not straightforwardly anyway. So in this case, we would expect to have higher levels of jitter in our preempting task here, because sometimes this task is going to interrupt a TTC task, and sometimes this task is going to be triggered from idle mode. So we would expect in general in a TTH scheduler, unless we take other action to prevent this, we would expect to see a significantly higher level of jitter in our TTH scheduler when compared with our TTC scheduler. One of the reasons for that jitter is the variable instruction length in a processor. So if we've got a processor in sleep mode or idle mode, then we would expect to have a fixed interrupt service time. If we have instructions of variable length in our processor and an interrupt is generated, we basically generally have to wait until the currently executing instruction is completed before we can trigger the ISR. This is one of the causes of a variation in jitter in a TTH scheduler when compared with a TTC scheduler. But we can address this problem. So let's just look at the nature of the problem first. So we have a TTC scheduler with idle mode, we get 0 jitter. If we have a TTC scheduler without idle mode, we get about 0.2 microsecond of jitter in this case. If we have a TTH scheduler with a long TTC task and we're still using idle mode in our schedule, we've got a long TTC task, we're getting round about half a microsecond of jitter from this design. Half a microsecond may not seem like very much jitter, but it may be more jitter than we wish to handle in this particular system. So what can we do? Typically what we can do is incorporate a pre-tick into our TTH scheduler. So in our TTH scheduler in this case, we have a pre-tick before the main processor tick. So we have a pre-tick after which we force the processor into idle mode, and then once it's in idle mode, the main processor tick takes place. So this, by putting the pre-tick into our code, we ensure that whenever the main processor tick is generated, the system is always in the same state. So the system hardware is always in the same state when our main processor tick is generated. So this is an example of what happens when we include an idle task or a pre-tick into our TTH scheduler. So we can then, in this case, we can reduce the jitter level down to the same level that we saw with a TTC scheduler. You might like to have a look in the book, in the appendices in the book, to see detailed code examples as to how you can achieve 0 levels of tick jitter in a TTH scheduler. The end result is that in a TTH scheduler we can control the levels of tick jitter very precisely. This is a general example. More generally, we can control the timing behavior in a TT design very precisely. So we can control and model the timing behavior in a TT design even when we have task preemption. With an equivalent RTOS-based design, the control of timing is usually comparatively limited. Let's look at one more example of this. So we saw earlier in this video that if we have a set of tasks and they have different priority levels and they have a number of shared resources, which could be shared data, shared components. Simply shared data in many cases is almost impossible to avoid in most practical systems. So if we have a set of tasks of this form of different priority, then we saw that we run the risk of priority inversion in our designs, and we have to use priority ceiling protocols and similar mechanisms to take control of priority inversion. But even with those, we cannot completely remove the problems of priority inversion from any system in which tasks can be released at random points in time. By comparison, TT systems can be rendered immune to the problems of priority inversion. It's not difficult to see why that is the case. So for example, let's assume that we have our three tasks here, A, B, and C, all sharing access to a particular ADC. So let's assume A is the highest priority task, B is a medium priority task, and C is a low priority task. So as we saw in an event trigger design with a conventional RTOS, we have to deal with the situation that task C may be using the ADC when task A requires it. What we do in a TT design is we try and avoid these collisions happening, and at runtime we can do checks like this. So for example, we know in advance when all of these tasks will be released. So at runtime, before task C accesses the ADC, it will ask the scheduler, can I use the ADC? And the scheduler will either say, yep, go ahead, use the ADC, there's nobody else scheduled to use it, or the scheduler will say, no, you can't use the ADC because task B, which is higher priority than you are, will require that ADC in 2 microseconds. Therefore, you'll need to wait, please, so that task B gains access to the resource when it requires it. That sounds like a complicated exchange and discussion. We can see the concept is straightforward. We know when the tasks are going to be released, so we can ensure that task C doesn't access the ADC at a time when a higher priority task might require such access. In practice, it's very easy to obtain this behavior. So here's a protocol that we call the time resource access protocol. And to work out whether a system has time to access a resource or not, we simply check with the scheduler how long it is until we get to the next tick. If we don't have time to access the resource, then our low priority task will not access that resource before the tick takes place. So essentially what we'll do is a low priority task will check with the scheduler whether it has time to access the resource. If it doesn't have time to access the resource, it will suspend itself, allowing the higher priority task to gain access to the resource. You might like to look at some more detailed code examples about this matter, which are in the ERES2 book. We can have additional levels of task priority. In a time-triggered hybrid scheduler, we have 2 levels of task priority. In a TTP, time-triggered preemptive scheduler, we typically have 3 levels of task priority, but we can have higher levels of task priority. So we simply add additional timers. We add an additional timer to the system in this case, which might run more frequently than the other timer. So we have a update to the H scheduler that might run every millisecond, and we have another higher priority timer tick that in this case runs every 100 microseconds, and we can run other tasks from that tick. So we can add different levels of task priority to the system, and all of these will be time triggered in this kind of design. In practice, I have never beyond a demonstration system used more than a TTP scheduler with 3 levels of task priority in a TT design. But in theory, we can use any number of levels of task priority in a TT design. So let's just wrap up this session by comparing the ET and TT modeling approaches. So when we're comparing a rate monotonic model and a TT model, we can consider the situation as follows. So we're asking the question, can we schedule this task set using an RTOS? If we use a rate monotonic model, we'll come back with the answer, possibly. if your processor utilization is less than 69% and you have independent tasks and you accept that the deadline is equal to the period. So your answer will come back saying, okay, you can probably schedule this if your processor utilization is less than 69%. In practice, if you keep the processor utilization, the CPU load, average CPU load to about 50%, you'll probably be okay in most RTOS-based designs. The approach with a TT design is a little different. When we ask whether we can schedule this task set using a TT platform, the TT answer will be yes, you can schedule the task set, and here's the tick list for detailed analysis. So we need to create a tick list. But once we've got that tick list, we can answer this question very precisely. In some cases, we can handle very high CPU loads from our system, and it's important to bear in mind that the scheduler load for a TT scheduler is typically much lower than it will be for a conventional RTOS. So the answer will either come back from the scheduling processes schedulability test that we've discussed earlier in this course. Either we'll be told, yep, you can schedule this task set and here's a tick list for detailed analysis, or you'll get the answer back, no, you cannot schedule the task set. And here's a tick list that highlights the problematic tasks. So if you find you've got some tasks that have a long worst case execution time and they're making it impossible to schedule the task set, you may be able to consider the tasks that have the long worst case execution time, revise these, and try the schedulability test again. So there are two different ways of approaching this. The RM approach, where we simply have to work out the processor utilization, looks very straightforward and gives us a simple measure of schedulability, but there are some assumptions that underlie that simple model that simply don't apply easily in practice. So we can only use an approximation of an RM model. In a TT case, we have to do a little more work to create a tick list, but once we've created that tick list, we get a great deal of confidence that answer to the questions about task set schedulability and answer to the question is whether we can schedule a given task set on a given platform and meet requirements such as jitter, response time, etc. We get a clear answer to those questions through the use of a detailed model and a tick list. So let's look slightly more generally at an event-triggered design. So if we have a set of world events, for example, switch presses, CAN messages, A to D conversions, in an event-triggered design, these world events are represented in our system by interrupts. So our system then becomes dominated by interrupt handling. One way of viewing this is that you're giving the world control of your system. To understand what I mean by that, let's consider a time-triggered alternative. So we still have the same world events, but we access and deal with those events by polling. And it's important to appreciate that as far as the user is concerned, the external operation of the system is exactly the same as a working ET version in normal operation. But if something goes wrong in the time trigger design, we can detect this much more easily, and we're always in control. We're not handing over control to the external interrupts. The TT system remains in control. For example, if particular switch presses happen at some very high rate, we handle that clearly. We are not going to suddenly trigger a very rapid stream of interrupts. In our TT design, we're simply going to pull the switch, find that something's happening, and deal with that scenario. We remain in control at all times. That's a comfortable place to be if you're developing a safety-related system. That brings us to the end of this video. Please read Chapter 27 and Chapter 28 in the ERES2 book before you continue with the course. Thank you for watching.